Welcome back to The Explainer. I want you to imagine a student who's just finished millions of grueling training steps. Once all that hard work is done, their abstract, hard-earned intelligence is finally crystallized and exported into permanent files. These very files dictate exactly how the AI reads your prompts. So today, we're going to unpack the permanent identity of an artificial mind, step by step.
Okay, let's dive into this. When the training engine finally stops, we're basically left with two distinct paths. On one side, you have the large language model. That's a symbolic brain built on language patterns, outputting 9 key files. But on the other side, we have the diffusion model. That's a geometric brain processing noise using entirely different structures like UNet and VAE files. Two totally different brains running two different systems.
For our language models, everything really hinges on the runtime brain. Literally every single time you hit send on a prompt, the inference engine springs into action and loads 6 essential files. Working together, these files act as the reading, thinking, and speaking systems for the AI. Let's take a look at exactly what these files are.
First up, we have the weights file. This is it, the actual core intelligence of the model. It's the brain itself. It's a massive file storing the attention matrices, feed-forward layers, embeddings, and you know those billions of parameters you're always hearing about? This is where the model's fundamental knowledge lives.
Next, we need a way for that massive brain to actually see our words. That brings us to the tokenizer and the vocabulary. You can think of this as the model's reader, its fundamental alphabet of thought. The tokenizer takes your human text and breaks it down into manageable chunks, or tokens. And the vocabulary maps those tokens into a numeric language the machine can actually process.
But wait, how does the AI know how to organize all this stuff? Well, that's the job of the config file. This is essentially the architectural blueprint. It explicitly tells the model how to assemble itself, defining the transformer layers, the attention heads, and the exact maximum sequence length it can handle at one time. Then we have special tokens. If the standard vocabulary is the alphabet, these special tokens are the grammar of control. Acting as the symbol table, they absolutely dictate the structural flow. Honestly, without these, the model would just be lost in an endless loop of text. They tell the model exactly when to begin, when to end, or when to mask specific pieces of text.
Now, what's really interesting about this part is where quantization comes in. Look, neural networks are huge, right? But these mathematical compression rules physically shrink the model's brain while brilliantly preserving its wisdom. This metadata dictates the bit width, the scaling, and the block sizes needed to run these massive models efficiently on regular, everyday hardware.
Finally, for the runtime brain, we have LoRa's and adapters. I like to think of these as optional plug-in mini brains. Instead of retraining a multi-billion parameter model from scratch just to teach it a new trick, you can just snap in these tiny delta updates. They grant the main intelligence highly specific, customized skills totally on the fly. Section 2. Training-only files. The learning memory.
Looking at this discarded memory, the very first file we find is the optimizer state. You can view this as the model's vital study notes. It captures exactly how the model learned over time, storing the momentum buffers, the gradient history, and the learning rate state. It is, quite literally, the footprint of the AI's educational journey.
Next, we have the training arguments. If the optimizer state is the study notes, this right here is the exact recipe used for the learning phase. It contains all the hyperparameters, the strict data set paths, and the training flags that govern the model's intense, heavy computational creation.
And the last training file is the checkpoint state. This acts as a rigid bookmark of evolution. It records the exact global step, the epoch number, and the scheduler state. If the training process crashed midway, which happens, this bookmark tells the supercomputer exactly where to pick back up, so absolutely no knowledge is lost.
So, that's how the AI was built. But let's move to and see how this builds in real time when you actually type a prompt. Step 1, the AI analyzes your input sentence. Step 2, the tokenizer mechanically chops your text into small token pieces. And step 3, it sends those pieces straight to the vocabulary.
The vocabulary itself is the model's absolute, rigid dictionary. It defines every single token the model is allowed to know. If it encounters an entirely new unknown word, it doesn't just panic. It automatically shatters that word down into smaller subword chunks that it actually does recognize. Once the text is shattered into tokens, it undergoes mapping. A raw text token is mapped directly to a numeric ID. For instance, a word might become 1432 or maybe 5256.
This is a critical barrier to understand, guys. The neural network is completely blind to human letters. It can only process numbers.
So, the crucial point is that this brings us to the threshold of embeddings. Raw numbers like 1432 mean absolutely nothing on their own. Embeddings convert these raw numeric IDs into dense mathematical vectors. This is the magical threshold where lifeless numbers finally, brilliantly turn into actual contextual meaning.
But there's a catch. Transformers read all these embeddings in parallel, all at the exact same time. So positional encoding is required to inject sequential order into that meaning. By using mathematical sine waves or rotary techniques like rope, the model finally understands which word came first and which came last. And this brilliantly illustrates the final assembly. The tokens align, the dense embeddings are added, and the positional encoding is applied. Together, they fuse to form the final sequence matrix. This matrix is the ultimate perfected input stream. It's the model's actual complete reading path.
We've traced the entire journey, from discarded training memories to the precise mechanics of tokenization, mapping, and sequence construction. The AI has successfully, flawlessly read your prompt. But this leaves us staring at an incredible threshold. Now that the mathematical matrix is built, how does this neural network actually start to think, reason, and predict its very next word?